Hello friends, welcome back to Arthvimarsh. In this video, I'm going to show you how to derive the consumer equilibrium condition. Now, to begin with the derivation of the consumer equilibrium, we have to first of all look into what is already given to us and what we are trying to basically aim at in terms of our objective. So, the market prices are already given in the market, and the income of the consumer is already given. As per our previous discussions, we have already discussed that we know that for instance you were going to buy a combination of commodities in the market, so corresponding to that we had prices, right? P1 and P2 corresponding to X1 and X2 commodities, and there was a budget constraint with the consumer which we denoted as M as a function of P1 X1 plus price time quantity of X2. The consumer was spending his budget among these two commodities given their prices. Now likewise here, when we are looking into the derivation of the equilibrium condition, uh, we are given the market prices and the income, and the objective is to maximize the utility here. Okay, and you know that your utility was a function of your quantity only, right? So now before we get into the derivation, there are few key assumptions which we need to understand, and that is there are n commodities which are available in the market with prices P1, P2, P3, so on up to Pn for the respective commodities. So initially we had been discussing in the XY plane that we had two commodities X1 and X2, for which we were discussing our budget constraint M as a function of P1 X1 plus P2 X2, right? But now we are saying that we are considering a general case because we are looking into the derivation, right? So we are considering n commodities. So here you can think of it like X1, X2, so on up to Xn. All right, and the prices corresponding to this are P1, P2, so on up to Pn. So this is what we are assuming, and the consumer has money income M, like we used to have for two commodity case. So we have money income, which is again a function which is being spent into price times commodity, so on up to Pn Xn, right? So this is given. So given this, we can write our problem for for deriving the equilibrium as that we want to maximize, what? We want to maximize our utility, right? So maximize utility as a function of our quantity, right? Uh, which is X1, X2, so on up to Xn, right? So we want to maximize this subjecting to what? Subjecting to, okay, we want to maximize the utility here subjecting to our budget constraint, right? And what was our budget constraint? Subjecting to our budget constraint, which I can write as a function of price time quantity, right? So wherein my I goes from 1 to n, sigma I 1 to n, quantity times price, or which we can expand as quantity time price, so on up to n commodities, right? Which is equal to M only, which I was talking about, like this only. Here X1 I have just changed with Q1, or I'll keep it that way only, which would be easy to relate for you as well. So we can write this as quantity times price, and this is X and Pn, right? So this is X naught, and don't confuse it with n, this is X only. So this is X and Pn. So this is what constraint we have in our hand right now, right? And we are going to understand that how do we go about maximizing this equilibrium condition using one of the key method, which is known as the Langrange multiplier method. Okay, so it's called the Langrange multiplier method. We are going to use this approach to derive the equilibrium of a consumer, okay, the condition for equilibrium of a consumer. So let's proceed. Now, for the derivation, we use the following steps which are involved in the Langrange multiplier method for the solution of the constraint maximization, because our objective is to maximize utility function, right, which was a function of uh, commodities, which were n number of commodities, subjecting to the budget constraint, which was m equals price times quantity plus price time quantity 2, so on up to price time quantity n, right? So we want to maximize this, right, subjecting to this constraint. So following are the steps which are involved in this Langrange multiplier method for our constraint maximization problem, because we want to maximize here. That's why constraint maximization. The constraint means our budget constraint. Okay. So the first step involved in this is that we have to rewrite the constraint in the following form. So what is the form? So we rewrite the constraint as the quantity times price plus quantity times price 2, so on up to quantity n times price n minus m equals 0. So I don't think that there would be any doubt in this how we arrived at this, because we were given this equation, right? What we did, we transposed this to the right hand side and our constraint becomes this, right? The budget constraint. So this is the first step. Now what we do in the next step is that we have to multiply the constraint by a constant which is called lambda. Okay, so this is our constraint. Resulting constraint is this. Say for example, this is equation 1. So we now have to multiply it by a constant lambda, which is called the Langrange multiplier. So multiplying this constraint, what will we get? So let us see. It gives us simply lambda times, it gives us lambda times the quantity times price, so on up to the quantity n times the price n, right? This is xn pn, right? And sorry, yeah, this will be minus m as well. So this is what we get on multiplying the above constraint, right? Now the third step which is involved here, the third step, the step 3 is to subtract this second equation which we obtained, this constraint, from the utility function and obtain the composite function. Okay, so I'll write it for you. The objective here is now the third step is, I'm sorry, I wrote subject. Yeah, so it's subtract the above constraint from utility function. Okay, we are subtracting this constraint from the utility function to obtain what we call as composite function. Okay, so I think this would be clear now when I rewrite this expression. So what we are trying to emphasize on here is that we are going to subtract the constraint. Which constraint? Constraint 2. Okay, we are talking about 2 here, equation 2. We are going to subtract this from the utility function. What was our utility function? It is this, right? So we are going to subtract this and we will be obtaining the composite function. So and we will be denoting our composite function as phi, okay, or phi, which you call. So what will be the resulting expression or the equation? It can be given as follows. Okay, so our composite function, the resulting composite function, will be equal to our utility function minus the above constraint that is in the equation 2, that is lambda times quantity times price plus quantity times price of second commodity, so on up to n commodities, because we are considering the general case for n number of commodities in the market that consumer is going to the market
There are n number of commodities available and they have corresponding prices associated with them from P1 so on up to Pn for the respective commodities. And yeah, there will be minus m here as well, because we are subtracting this expression from the utility function. So utility function is here u, which is in turn a function of the quantities, right? So this we can call as expression 3, right? Now what we are trying to do here is the maximization of the composite function. Basically it implies the maximization of the utility function. Now how to go about showing this? So maximization of the composite function, and you know what was our composite function, that is phi, right? So maximization of phi basically implies maximization of utility function. Now how to show this? Okay, so we are going to look into this. Now the first condition for maximization of any function is that its partial derivative is equal to 0, right? So for any function, I mean, this is the rule, general rule of differentiation, right? So differentiating phi, so what we are going to do is differentiating the composite function phi, okay, with respect to what? With respect to the quantity x1 so on up to xn, right? And lambda. We are going to do this and equate to 0. We get what? Because why are we doing this? Remember that because I mean it's the general rule of differentiation that first order condition, okay, for maximization of a function is that its partial derivative is equal to 0. This is the reason for this, right? So in order to maximize our utility function, I mean, we are going to go into the maximization of our composite function, which we had derived in the previous step. So we will be differentiating that phi function with respect to the quantities and lambda and equate it to 0. All right, so we are going to do that. I'll rewrite the expression of phi which we had obtained in the previous step. We had phi equal to the utility function minus lambda times quantity times price plus quantity times price so on up to quantity n price n minus m, right? So this is the expression which we had in our derivation. So given this, now we are going to differentiate this expression basically with respect to the quantities and with respect to lambda. We are going to differentiate with respect to this x1 x2 so on up to xn and with respect to lambda. Okay, so let's move to next page to so now I'll rewrite it again so that it's easier. So phi is given as u minus lambda times quantity times price plus quantity times price so on up to Pn minus m, right? So this expression we already have and we are differentiating it with respect to quantity and the lambda, that is the Langrange multiplier. So first of all, differentiating it with respect to quantities, so what we will get is d phi or del phi upon del x1, which will be equal to del u upon del x1, right? And minus minus this expression we are differentiating, so it will give us lambda times, because we are differentiating with respect to x1, so it will give us lambda times p1, right, equal to 0. Likewise, if we are differentiating this with respect to second commodity, it will give us du upon del x2 minus lambda time p2 equals 0. And likewise, so on up to n, this will be the case, right? If I am differentiating del phi with respect to del xn, I will be getting the differentiation del u upon del xn minus lambda pn equals 0, right? So this will be the case so on up to n commodities. And similarly, now we recall, if you recall, that we were differentiating with respect to the quantities, and also with respect to lambda we have to differentiate. So this is with respect to the quantities. Now differentiating with respect to lambda, what does it give? Differentiating with respect to differentiating the composite function, the del phi, with respect to del lambda, it will give us what? It will give us minus of the entire function, I mean the constraint function, right, p1 plus x2 p2 plus so on up to xn pn minus m, right? And this will again be equal to 0, the basic rule of differentiation, right? Now given these equations, say for instance I call these entire expressions as let's call these as 3 and this as 4. Okay, now given these expressions, okay, now from the equation, from the equation 3 and 4, what we get is, now recall, on partially differentiating with respect to quantity, we know the expression was the differentiation of the composite function with respect to the quantity, or x1, which we had, was equal to the differentiate, I mean of the utility function, and the with respect to x1 minus lambda p1, right, equal to 0. Now this can be written as, pay attention here, that del u upon del x1 equal to lambda p1, right? I can write it in this form. Likewise, for the second differentiation which I had done was del with respect to the second commodity, which was del u upon del x2, right, and minus lambda p2 equal to 0, which implies, or which we can write as del u upon del x2 equal to lambda p2. We are just transposing this lambda towards this side from this expression, right? So this is what is being rewritten for all these cases. So this can go on up to, so I mean n number of cases, right? So for the nth case, del phi upon del xn, it will be giving us del xn minus lambda pn equals 0, which implies del u upon del xn equals lambda pn, right? So likewise, I mean this keeps on going, right? But if you recall, now pay attention here, but we know that del u upon del q1 or del u upon del x1, right? So del u upon del x1, what is that? Recall, say for instance, this is your utility function as a function of quantity 1, quantity 2, so on up to quantity n. Okay, for a given utility function, if you differentiate this utility function with respect to a particular quantity, like for example, when we talked about the two commodity case, if this was your utility function, and if you mentioned that change in your utility with respect to the change in x1, what does that mean? That meant it's the marginal utility of x1, right? If I increase your consumption of x1 by 1 unit, how much change in your utility is going to be there, right? So it's the marginal utility, right? This expression of change in utility with respect to the change in the quantity, right? So likewise, if you relate it here, this del u upon del x1 is giving me what? It's the marginal utility of commodity 1, right? It's the marginal utility of 1. Likewise, in this expression, it's the marginal utility of 2, right? It's the marginal utility of 2. So But I mean, from this discussion, we know that del u upon del x1, okay, is the marginal utility of 1. Del u upon del x2 is the marginal utility of 2, so on up to how many cases we had? We had it till n, right? So for del u upon del xn, it's obviously again equal to the marginal utility of n. Now given this, okay, I am writing it as expression 5. Now pay attention here. I'm writing it as 5. Now based on the results in 5, what I can do is, so we know that those expressions are equal to the marginal utilities, right? So substituting and solving for lambda, okay, what we get is, we are solving here for lambda, okay, and what we are getting here is that your lambda is going to be equal to what? Marginal utility upon the price for the commodity 1, because you know that mu1 was equal to what? Mu1 was equal to what? If you recall the expression, because your mu1 was equal to your ratio of del u upon del q1, right? So this is what we had in the previous expression, right? Given this ratio, I can rewrite my lambda as the ratio of the marginal utility with respect to price, because in the lambda expression for the first commodity, what we had del u upon del x1, sorry, it's x1, right? So del u upon del x1 equal to lambda times p1. This was the expression we had initially, right? And we said that we know that this is equal to the marginal utility, the ratio of the utility, right, with respect to the change in the commodity. So we wrote this expression as the marginal utility, and this is equal to lambda, so we are just transposing this p, okay, to the denominator. So we get this expression which I have listed here in terms of lambda, right? So this is what we get for the first commodity, and likewise we get lambda equals marginal utility of 2 upon p2, so on up to how many commodities? N, right, upon pn. So this is the expression which we obtained in terms of lambda. So I can write this result, this entire result can be written as, pay attention here, that lambda, because this is all equal to lambda, so lambda equals mu1 upon p1, that is the ratio of the marginal utility to that of the price for commodity 1, is equal to that of the ratio of the marginal utility to that of the price 2, is equal to mu3 upon p3, so on up to mun upon pn, right? So this result I am getting out from this. So my lambda, Lagrange multiplier, is having this interpretation here, right? Or alternate. Now, given that we have derived our expression of lambda as the ratio of the marginal utility to that of the prices, so on up to mun upon pn, right? So we have derived this expression. Now what we are saying that alternatively, I mean, we may derive this expression corresponding to each commodity x, I mean, which is under consideration, x1 so on up to xn, by the equation which refers to commodity y, right? So in a xy plane, say for example, this is commodity x, this is commodity y, I mean, in the two commodity case, okay, in the two commodity case, how can we write this expression as? Because if you now recall that in our discussion so far, we always have been considering the case of two commodities x1 and x2, right, to simplify our understanding and interpretations in a 2D plane, right? So for two commodities, obviously, how can you rewrite this? So you can write up till two commodities as mu1 upon p1 equal to mu2 upon p2. This will be your equation, right? So what we observe is that the equilibrium conditions, okay, they are identical. I mean, in the cardinalist approach, if you would have observed that similar expression is there, right? And I mean, when we are giving the example of the equilibrium there in the book as well, in the Halvarian, you will find that for two commodity case, when we were having the discussion, I mean, the expression is similar to that in this approach. Okay, so I mean the result. So in both the theories, the cardinalist or the indifference curve approach, we have the same expression, right? So it's mu1 ratio of the marginal utility to that of the prices, right? So and this is again equal to so on up to mu of x upon p of x. I mean, in general form, if you have to write mu y upon p of y, I mean, it can be any among any commodity. It can be commodity 1 and 5, 1, 2, 5 or 7, any commodity, right? So this expression will hold. And this is what we call basically as the I mean, condition of equilibrium in general form. Okay, so always remember this expression of equilibrium condition. Okay, so this is it about the derivation. And just to point out one more thing, that if you recall, what is the meaning of, I mean, say for instance, I transpose I mean, I tweak this expression, okay, in this expression 6, and I do it in a way that I transpose the marginal utilities on one side, okay, mu of y equal to the p of x upon p of y. If I transpose the expression, okay, simply, so what I get now, this is the ratio of the marginal utilities, right? And this is the ratio of the prices, right? And what is the ratio of marginal utilities? What do we call that? If you remember, the ratio of prices also, what do we call that? If you remember your indifference curve and the budget constraint examples which we have been discussing, we know that the slope of an indifference curve is what? It's the marginal rate of substitution, right? The slope of the indifference curve, right? So and what is the slope of the budget line? It's the ratio of the prices, right? It's the ratio of the prices, px upon py. If this is x and this is y, so the slope of the budget line is given as px upon py, right? And the slope of a budget, I mean, indifference curve, we know that it's the marginal rate of substitution, which is equal to the ratio of the marginal utilities, right? So this is what we are getting in this expression, right? And now if you recall, I mean, if you can relate it with this, that I mean, this condition is implying this point basically, because this is equal, right? So your MRS is equal to the slope of the budget line here, right? MRS is equal to the slope of the budget line, which is the condition of equilibrium basically. This is the condition of equilibrium, right? Of the consumer equilibrium. So this is what I wanted to, I mean, summarize here, that this expression, this is equal to what? This is equal to the marginal rate of substitution of commodity x and y. Now the general expression which we have derived here, like so on up to n commodities, I mean, this is for n commodities, right? So you can write for n number of commodities here, right? It's equal to the MRS only for the n commodities. So this is about it. So the concept of marginal utility, which is implicit in the definition of the slope of the indifference curve, you know why it's implicit in its definition? Because the slope of the indifference curve is marginal rate of substitution, which is equal to ratio of the marginal utility of one to that of the other, right? So and its measurement is also not required, right? By this approach, you don't have to measure that. So this is all about this derivation. Okay, so all you need is a diminishing marginal rate of substitution, okay, which of course does not require diminishing marginal utilities here of the commodities involved in the utility function. So this is all about the derivation. So just to give you the final expression of what the condition of equilibrium looks like, was that your ratio of the marginal utility of the commodities which were under consideration was equal to the ratio of the prices, Okay, and in a xy plane, when we were discussing about all this, we can rewrite it as mu x upon mu y equal to price of what? Price of x to that of price of y, and is equal to the marginal rate of substitution for what? For x and y, right? And what it's implying is simply this condition of the consumer equilibrium, which we were seeing diagrammatically for n number of cases, like for perfect substitutes, complement, the condition of tangency basically, right? And this was the point of equilibrium. This is the indifference curve. You know the slope of indifference curve is what? Indifference curve slope is equal to marginal rate of substitution, right? And the slope of this budget line is equal to what? Ratio of the price. If this is x1, this is x2, so definitely it's going to be p1 upon p2, right? This is the slope. So this is all about this consumer theory, okay? In terms of deriving the equilibrium. So thank you so much.
If you like the content of this video, please do like, subscribe and share our channel so that we keep coming up with such content in future. Thank you.